well, then let's finish off the fundamental counting principle this evening. What I want to talk to you about tonight are two ideas. The first one is the arrangement of objects in a row. And then once we've finished discussing that, then I want to show you how we would involve probability, okay? Because they can ask you sort of a combination of the two, where objects are arranged in a row together with probability. All right, so the first example that we are going to look at is 3 boys and 2 girls, right? So it first asks us, now remember, people cannot be repeated like letters and like numbers. All right, so we're going to use factorial notation. The first question says to us, in how many ways can 3 boys and 2 girls sit in a row? Now, they're not saying that the boys and the girls have to sit together. They're just saying in how many ways can these 5 people sit together in a row? What do you guys think? In how many ways can the 5 people sit together in a row? That's it, Trish. Perfect. Okay, so it would be 5 factorial ways that they can sit together. So that would be 120 ways. Lovely. Well done. Okay. Now they start placing some conditions on the way in which they sit with each other. So in the first, well, that's part A. So in part B, question B, they say, in how many ways can they sit in a row if a boy and his girlfriend have to sit together? So what we have to do is this. We have to put that boy and that girl together. So they can sit boy, girl, but they could also sit girl, boy. So we would say here that there are 2 factorial ways that they sit with each other. Then what we do is we put them together in a group. Right, and then we arrange that group with the other objects in the row. So the other objects in the row are the 2 remaining boys, and there's 1 more girl. So we're going to draw circles around them as well because they are objects in their own right. And then we count the number of circles that we've got. So we've got 4 circles, 1, 2, 3, 4, or 4 groups. So there are 4 factorial ways in which those groups can be arranged with each other. So it would be 2 factorial by 4 factorial. Exactly, Sihle. Okay, and we can work out what 2 factorial times 4 factorial is. We end up with 48. Okay, so 48 ways these people can sit together if a boy and his girlfriend are sitting together. All right, perfect. Well done. Okay, Lesedi, not a problem. I know this is difficult in the beginning. Okay, so the rest of you, if there are other people that feel they understand this and you want to have a look at questions C, D, E, and F, you're welcome to. I'm just going to explain this again for Lesedi because I'm sure there's other people that don't understand it. Okay, so this is how we do it, Lesedi. Right, I'll just rub that out and we'll do it again. All right, so look at it like this, Lesedi. You have got 3 boys and 2 girls. So now a particular boy and a particular girl have to sit together. We put them together as a group. They can sit boy, girl, but they could also sit girl, boy. So there are 2 factorial ways in which they are arranged with each other. Now there are 2 boys left over, a boy and another girl. So now we count the number of ways in which these 4 groups can be arranged together, because what we can do here, Lesedi, is we can arrange it in like a sliding row. So in other words, we can have the boy-girl grouped together, boy, boy, and then a girl. Or what can happen in our second row, so let's just get this down, boy, girl, boy, boy, girl. So then what they can do is they can sit together in the first position. Then a boy can sit over here. Then we can have boy, girl. and then we can have a boy over here, and then the girl at the end. Or we could have a boy at the front and another boy at the front, and then we can have the boy-girl combination over here with a girl at the end. Or we could have the boy and a girl and a boy-girl, sorry, boy-girl combination at the end. All right, so it slides down like that. All right, so there are 4 factorial ways in which the boy-girl combination can be arranged with everybody else. So that's why we say 2 factorial, sorry, by 4 factorial. Okay, which is 48 ways. Okay, no problem, Lesedi. I'm glad that makes more sense. Okay, so let's have a look at some of the other conditions that they impose upon us. All right, so in question C, they say, in how many ways can they sit in a row if the boys and the girls have to sit with each other? So now what they're implying in question C is that the 3 boys need to sit together as a group, and the 2 girls need to sit together as a group. There are 3 factorial ways that the boys can be arranged with each other. There are 2 factorial ways the girls can be arranged with each other. And then there are 2 factorial ways that the groups can be arranged with each other. So it's going to be 3 factorial by 2 factorial by 2 factorial. Okay, which is 24 ways. Okay. Now in question D, they said, in how many ways can they sit in a row if just the girls are to sit together? So we've got to have the girls together as a group. And now we've got 3 boys with whom they can be arranged. So it'll be 2 factorial by 4 factorial. Okay, so that would also be 48 ways. Is that making sense to everybody? Is everyone all right? Any questions so far? Okay, thank you for your responses. All right, so most people seem to be okay. Chloe, I know it's not the easiest thing to understand, but if we do this a little bit more, hopefully it'll become a little bit easier for you as we move through the work. Okay, so we were up to question E by now. So now they say, in how many ways can they sit in a row if just the boys are to sit together? So now we have been told we've got to put the boys together. There are 2 girls remaining. So there are 3 factorial ways in which the boys can sit with each other by 3 factorial ways in which the group of boys can be arranged with the remaining girls. Okay, so this would give us 36 ways in which they can be arranged if just the boys are to sit together. All right, now the last question says, in how many ways can they sit in a row if the boys and girls are to alternate? So the boys and the girls need to alternate. So what they mean here, sorry, let me just move these questions down. Let's go back up here. All right, so the only way that this can happen, because there's an odd number of boys and an even number of girls, is for them to go boy, girl, boy, girl, boy. So you've seen me before using blocks. And I think that when we fill the blocks with this question, it makes sense as to what the answer is going to be. Okay. So it has to be boy, girl, boy, girl, boy. It can't be anything else. It's the only way that they can alternate. So if we consider the first block, block number 1, where the arrow is, in how many ways can we fill that first block? How many ways can we fill this first block here? It has to be a boy. So we have a choice of 3. Beautiful. 3 boys. Now a boy is gone. In the second place over here, it has to be a girl. How many girls do we have to choose from? There we go, Iletu. Good. Well done. 2 girls. Now a girl is gone. There are 2 boys left. So in how many ways can we fill the third block? That's it. 2 ways. Good. So now another boy is gone. There's only 1 girl left. So there's only 1 way that we can fill this block. And again, there's only 1 boy left. So there's only 1 way that we can fill that block as well. Okay, so we've got 3 times 2 times 2 times 1 times 1. Or if we want to, we can write this as 3 factorial. 3 times 2 times 1 times 2 factorial, because you've got a 2 times 1. Okay, so you can write it in either of these 2 ways, either using factorial notation or not if you don't want to. Okay, but yes, it would be 12 ways. Does that make sense to everybody? Are there any questions? Any questions? Makes sense. Okay. Good, Ayola. I'm glad to hear that. All right. In that case, let's move on and let's talk about something else. Okay. So what we're going to do is we're going to have a look. They like to use examples of books. So we're going to talk about those now. Let me just move these down. I don't know why this is all on top of one another, but anyway, it doesn't matter. Okay. Okay. So we're going to look at question number 5. Okay. In this situation, we have 4 maths books, 3 history books, 3 science books, and 2 biology books. In how many ways can they be arranged on a shelf? Let's just scooch over and create a bit more space here. There we go. All right, so in part A, what do you think? In how many ways can they be arranged? Okay, so Litlu says 12 factorial. Where did you get 12 factorial from, Litlu? Trish says 12 factorial. Okay, because there are 12 books. So 4 plus 3 is 7. 7 plus 3 is 10, plus 2 is biology books. They did not tell us that certain books needed to be together. That's it. You added the number of books together. Beautiful. Okay, so we've got 12 factorial, which is some really big number. So we'll just leave it as 12 factorial. Okay. Now they say to us, in how many ways can they be arranged on the shelf so that all the books of the same subject are together? So again, I want you to think about this a little bit, and then you can DM either myself or Yolanda an answer. In how many ways can they be arranged if the subjects have to be together? What do you guys think? Okay, so Trish, what you're saying is much bigger than everybody else. I think that's what I would say. So I'm just going to convert from factorial notation to a number. Okay, so Trish, I'm getting the same as you. Lehlu, I'm getting the same as you. Katleho, Zoom user, Sihle, you're all getting 1728. So I'm just interested, where does the 1728 come from? How do you get 1728? What are you doing? That's it, Keithlyn. Chloe, let's have a look. What are you saying? Okay, so Chloe, there's just one. Yes, you do. You do. Chloe, that's good. Well done. That's exactly right. Keith Lynn, perfect. Claire, yes. Danelle, yes. Okay. So, yes, let's just have a look. Miss Cindy, yes. Lucidi, yes. Okay, good. All right. So the four mathematics books can be arranged in 4 factorial ways. The 3 history books can be arranged in 3 factorial ways. The 3 science books can be arranged in 3 factorial ways, and the 2 biology books can be arranged in 2 factorial ways. There are 4 groups of books, so there is an additional 4 factorial ways in which those groups can be arranged with each other. So quite right, it is 41,472 ways in which they can be arranged if subjects of the same are put together. Okay, good. Well done, everybody. Are there any questions before we have a look at the next question? We're all happy with that. All right, cool. So let's have a look at question number 6. Here they ask us to find the number of ways in which 6 people can ride a toboggan if one of a selected 3 has to drive. The number of ways in which 6 people can ride a toboggan if one of a selected 3 has to drive. What do you think? So in other words, we have to have a driver. Then we've got everybody else. Okay, so in how many ways can we fill the driver's seat? In how many ways can we fill the driver's seat? No, we can't fill the driver's seat in 6 ways. Remember, it says here, that's it, Chloe. All right, it's only if one from a selected 3 can drive. So how many ways can we fill the driver's seat? We can only, so some of you sent the right answer. There are, let's just have a look. That's it. Okay, and Tukazi, Masindi, yes. Some of the others also saying 3 as well. There are 3 ways in which we can fill the driver's seat. If the driver's seat is taken, how many people are left? How many people are left? That's it, iPhone. There are 5 people left. Yes, Miss Cindy. All right, so the rest of the toboggan can be filled with 5. Oh, sorry. The number of ways in which 6 people can ride if a toboggan is, if one, yeah, so it would be like that. Okay, because they didn't tell us how the remaining people could be seated. All right, so there would be 5 factorial ways in which they can be arranged with each other. So it would be 3 by 5 factorial. Does that make sense to everybody? So there would be 360 ways. Okay, why isn't it 3 factorial? Because it's not 3 times 2 times 1. Okay, it's one of 3 people. Okay, so there are 3 different ways in which you can fill that first slot, not 3 by 2 by 1. Okay, Oratila did not get that. Anybody else struggling with this question? I'm happy to explain it again. All right, so there's a couple of people asking, not a problem. Let me explain it again. Okay, so there are 6 people that are riding a toboggan. Do you know what a toboggan is? It's actually a strange question to have in a South African textbook. Does anybody know what a toboggan is?
I really don't know myself.
Don't you
I was
know? Okay,
wondering
all
what
right. Well,
this.
actually, see, Wasitli says no. Shisana says no. There we go. Sihawa knows. So Sihawa sent me the answer. You're quite right, Sihawa. Well done. Okay. A toboggan is a sled. Yes, that's it, Swanaka. It's a sled. Okay.
A
So
sled.
a sled, yes. You know,
So,
like that you would get into and ride on snow? That's what a
yeah.
toboggan. That's what a toboggan is.
Wow.
Okay, so there's our toboggan, and normally what the people mainly used by kids, yes, Swanaka. So in other words, what we've got, I mean, who knows where the driver sits, but let's pretend that the driver sits at the front. Okay, and then we've got this space in the rear where people are going to sit one behind each other. So we've got one driver, and then because it can fit 6 people, we've got 1, 2, 3, 4, 5 people that we can fit in behind the driver, right? Now, there are only 3 people that can drive. All right. So we have a choice of how many people to fill the driver's seat. It tells us if only one of a selected 3 must drive. So the driver's seat can be filled in 3 ways, not 3 factorial ways. Okay, because we're not filling the driver's seat more than once. Okay, it's just in one way that the driver's seat can be filled. The driver, it's one seat, but it can be filled by 1 of 3 people. So there's 3 ways in which the driver's seat can be filled. Okay, when the driver's seat is filled, all right, that leaves 5 people that need to sit down. Okay, so there would be 5 factorial ways in which you can fill these blocks over here. Because obviously if one person sits down, there'd be 4 people to fill the second seat, 3 people to fill the third seat, 2 people to fill the last seat, and 1 person to fill the last seat. So that's why it's 3 by 5 factorial. The driver's seat can be filled in 3 ways, not 3 factorial ways, 3 ways. Does that make sense? Okay. So 1 of a selected 3 must drive. So there are 3 ways in which that first seat can be filled. All right, then the remaining 5 people are arranged in 5. Yes, because there's 6 people. So the driver together with the other 5 makes 6 people, iPhone. Okay, so there's the first person, the driver, the second person, the third person, the fourth person, the fifth person, and the 6th person. No, because in Konaiza, there's only 3 ways in which you can fill the driver's seat. When the driver's seat is filled by one of those 3 people, you've got 5 people waiting to fill the remaining seats. Okay, there are 5 seats left over. There's 5 people, so they can be filled in 5 factorial ways. Okay. That's the idea. Are we all right with this question? Yes, the passengers are the 5. Yes, yes, Nkoniza. Yes, yes. Because there's only one person sitting in the driver's seat. So in other words, the other 2 people that could have been drivers are now passengers. Okay. All right. Okay. Cool. I'm glad that that is all right. So what I'm going to do is I'm going to oh, that's got some probability questions in it. Okay. So what I'm going to do with you guys is this question very quickly. Okay. And then we'll go and we'll talk about some probability. Right. So the Gauteng government introduced a new license plate system in December 2010, the month it expected to run out of numbers to allocate under the old system. The number plates for most vehicles in Gauteng used to be created in the following way. So there used to be 3 letters, okay, excluding the vowels A, E, I, O, U, as well as Q, and they allowed repetition. Then it was followed by 3 digits, either a 0, a 1, 2, 3, 4, 5, 6, 7, 8, or 9, and repetition was allowed. Okay, so a license plate used to look like this. For example, YGG866. The latest number plates for Gauteng have been changed. The same letters and digits are used as before, but the structure is now different. So it goes 2 letters, 2 digits, 2 letters. Right now, the reason that the Gauteng department did this, all right, is so that they could have more number plates, right? Because they were running out of number plates. So the first question says, right, how many possible number plates were there with the old system? How many number plates were there with the old system? So remember, they've got rid of the vowels, and they also didn't use the letter Q for some bizarre reason. So how many possible number plates were there with the old system? In how many ways? So remember, we're filling 3 blocks that have letters and 3 blocks that have numbers. So how many how many letters are there to fill this first block? 20, good. Repetition is allowed. So in how many ways can they fill the second block? Still 20. Quite right. Repetition is allowed, so they can fill the last block also in 20 ways. The last 3 blocks are numbers. Repetition is allowed. That's at Shisana, quite right. So this is 10 by 10 by 10. So it would be 20 cubed times 10 cubed. All right, which I think someone sent me the answer. It's a huge, big number. 8 million. I don't know who it was who sent me that, but you are quite right. So there are 8 million different number plates that could be made under that old system. Then the Gauteng department said, hang on a second, we're now running out of license plates. We better change this. Let's see, did they make a wise decision? How many number plates can we make with the new system? So the new system is 2 letters, 2 numbers, and another 2 letters. Did they solve their problem? in how many ways can we fill our first block? Remember, repetition is allowed. So this would be 20 by 20. Okay, so they are excluding A, E, I, O, U. Okay, so they've excluded the A, the E, the I, the O, the U, as well as Q. So that's 6 letters that they've taken out of the alphabet. Okay, so that's where the 20 comes from, because 26 minus 20 leaves us with, 26 minus 6 leaves us with 20. Okay. Then here we've got 10 by 10, and then here we've got 20 by 20. That's it, Sihle. I'm sorry, Nkaniza. Yes, massive. Okay, so we've got 20 squared times 10 squared times 20 squared. All right, so they've doubled it. Okay, so that's it, 16 million. There we go. All right, so they were clever to go and change that. All right, so that's also a question that they can ask you. There we go. Cool, well done, everybody. All right, so let's spend a little bit of time talking about some examples that involve probability. Okay, and what I'm going to do is I'm going to use example number 2 as a way of being able to discuss this. Yes, Sihle, sorry, did I miss something?
Hi, ma'am.
Hi, Sihle.
Yes. Yay, I'm very lost. Can you please repeat that, please?
Oh, well, you're talking about this one over here, the number plates.
Yes, yes, ma'am.
Okay, all right. So Sihle, they changed the number plate system. So here they've got a letter and a letter times a number and another letter and another letter. So repetition is allowed. They have taken out A, E, I, O, U, and Q. So that's 6 letters. So from the 26 letters in the alphabet, they've removed 6, so they are working with 20, and they allow repetition. So that's why with 2 letters, we've got 20 times 20. By 2 numbers, there are 9 digits from 0 to 9. So that's 10 by 10. Sorry, there are 10 digits from 0 to 9 because we're including 0. And then there are 2 letters at the end. So that's why it's 20 by 20. Does that
Oh,
make
okay.
sense now? Okay, so that's
Yes,
why it's
ma'am.
20 by 20 for letter, then number. There are 10 and 10 because repetition is allowed. And then there's another 2 letters at the end. So it's letter, so it's 20 by 20 again.
Okay, thank you, ma'am.
Okay, no problem. All right, so we were looking at this question over here, the word clipboard. Now it asks us if the letters are arranged in any order without repetition to form different words, what is the probability that the word formed will start with a C and end with a D? Now, this question is different because now they're not asking us for the number of ways in which the letters can be arranged. They're asking us for probability. So when we calculate the probability of any event, okay, it's going to be the number in that particular event divided by the number in the sample. All right. So the probability that this word is going to start with a C and end with a D is going to be calculated as follows. First of all, let's calculate the number of possible ways in which the letters of the word clipboard can be arranged with one another. Now, remember, there's no repetition allowed. They're all different letters. So what is the total possible number of ways in which the letters of the word clipboard can be arranged? Good. 9 factorial. Lovely. 9 factorial. Good. Now let's think about the top. Okay. It has to start with a C. So in how many ways can I fill the first block? It has to start with a C. One way. Absolutely. It has to end with a D. So in how many ways can I fill the last block? Also one way. How many letters have I used? I've taken out the C and I've taken out the D. How many letters are remaining? That's it. So there would be 7 factorial ways in which those letters can be arranged with each other. Okay, so this would be 7 factorial over 9 factorial. Does that make sense to everybody? So 1 in 72 chance of the word starting with C and ending with AD. Okay, so Amahle, there are 9 letters, 9 different letters. So there are 9 factorial ways in which those letters can be arranged with each other because there is no repetition allowed. Where's the 3 factorial, Katleho? I'm not sure where 3 factorial comes into.
Ma'am,
Hello.
I was just asking. Oh, sorry, ma'am. Ma'am,
It's
I was just
okay.
asking because what's this? 7 factorial over 9 factorial is just the same as 3 factorial. Am I wrong? No, it's the same as 2. What? 3? No.
Okay, so oh, I see what you mean. So you're saying 7 by 6 by 5 by 4 by 3 by 2 by 1 at the top, and then at the bottom we've got 9 by 8 by 7 by 7 by 6 by 5 by 4 by 3 by 2 by 1. So the 1s cancel, the 2s cancel, the 3s cancel, the 4s cancel, the 5s cancel, the 6s cancel, the 7s cancel. So that's why it's 1 in 72. Okay, because you've got the 1 left over at the top, but you've got 9 times 8 at the bottom. Okay, Katleho?
Okay, ma'am. Okay.
Okay, all right, no problem. Now we need to calculate the probability that it's going to start with the letter O. So that means there is only one way in which the first block can be filled. If one letter is used, there are still 8 letters left over. So in how many ways can those 8 letters be arranged with each other? In how many ways can those? No. 8 factorial, that's it. So there are 8 factorial ways in which they can be arranged with each other. Good. Over the 9 factorial ways that all the letters can be arranged with each other. Okay, that's it. All right, so 1 over 9. Okay, is correct. Which one? B, iPhone 2? Okay. All right, so it has to start with the letter O. So if you go back and you look at the word clipboard, okay, we have to use the letter O in the first place. This is where the letter O is going to go. There are 1, 2, 3, 4, 5, 6, 7, 8 other letters that have to be arranged, and we're not allowed to repeat them. So there are 8 factorial ways in which those 8 letters can be arranged with each other. That's why we've got 1 times 8 factorial at the top. Okay, the 9 factorial is the number of letters that can be arranged with each other. So there are 9 letters in the word clipboard. So there are 9 factorial ways in which those 9 letters can be arranged with each other. Does that make more sense? No problem. Okay, so what I'm going to do now is I'm going to go down and I'm going to do this question with you in the time that we have remaining. I've seen this sort of question in exams, so that's why I wanted to do this one. Okay. So there are 7 different shirts and 4 different pairs of trousers in a cupboard. In 7A, they ask us, in how many different ways can the clothes be arranged on the rail? There are 7 different shirts and 4 different pairs of trousers. In how many ways can they be arranged on a rail, in a row? What do you think, guys? Good, 11 factorial. Nice, well done. Part B. In how many different ways can the clothes be arranged if all the shirts are to be hung next to each other and all the pairs of trousers are to be hung next to each other on the rail? So in how many different ways can the clothes use factorial notation? Good, Chloe. In Koniza, there's one thing you didn't consider. That's it. Let's say, oh, nice. Okay, good. So 7 factorial ways in which the shirts can be arranged, multiplied by 4 factorial ways in which the trousers can be arranged. Then remember, we put them into groups. So there are 2 factorial ways in which they can be arranged with each other. Okay. Okay, Lichlu. So 7 factorial times 4 factorial times 2 factorial. That's it. Good stuff. Question C. In how many ways can a pair of trousers hang at the beginning of the rail and a shirt will hang at the end? In how many ways can a pair of trousers hang at the beginning of the rail and a shirt at the end? So Inkonizer sent me an answer. In how many ways can a pair of trousers hang at the beginning? So you've got that first position, got your middle, and then we have to have something hanging at the end. So in the first position, it has to be a pair of trousers. In the last position, it has to be a shirt. Okay, so this is like the toboggan question in some respects. Okay, in how many ways can we fill the first position where the trousers go? We have a choice of how many? We have a choice of 4, exactly. Okay, because we have 4 pairs of trousers, quite right. So there are 4 ways in which we can fill the trousers. Then, if we consider the shirt hanging at the end, in how many ways, it's okay, no worries, iPhone 2. In how many ways can we fill this last position where the shirts go? We have a choice of 7. Good. All right. So now we've lost 1 trouser and we've lost one shirt. How many other objects are there that need to be arranged in a row? 1, 2, 3, 4, 5, 6, 7, 8, 9 things. They say nothing about how they need to be arranged with each other. Okay, but they're different shirts and different trousers. So that means that there are, good Jude, 9 factorial ways in which they can be arranged with each other. Okay, so for this question, it will be 4 by 9 factorial by 7. Whatever that is, 4 by, oh man, 4 by 9 factorial by 7. Oh, that's a big number. I don't even know if I would worry about working that out. 10 million. 160,000. Sorry, I'm sitting in the dark here and I can't see with my glasses on. Never mind off. 640,000. There we go. Good stuff. All right, let's finish these questions off. Let's go and have a look at question D. Now look, careful guys. What is the probability that a pair of trousers will hang at the beginning of the rail and a shirt will hang at the end of the rail? What do you think? What would we do? Oh, wow. But it says probability, okay, Oratile? So because it says probability, what do we need to do differently here? Okay, I disagree, Iola. It's not just... There we go, good. Anyone see the connection between question C and D? In question C, we calculated the number of ways in which we can hang a pair of trousers at the beginning and a shirt at the end. There we go. Good, Jude, you've got it. Okay, so the numerator is going to be the same as it was for C. 4 by 9 factorial by 7, because that's the number of ways in which we can hang a pair of trousers at the beginning and a shirt at the end. To get probability, we have to divide that by... That's it, Chloe. You've got it. Okay. Amahle, I don't know where the... Yeah, there we go. That's good. Well done, Amahle. Perfect. Okay. Over 11 factorial. Because there were 11 factorial ways in which we can hang the pieces of clothing together. So here we should be getting 14 out of 55. That's it, Chloe. Good job. Okay. Now, in the last example, yes. Okay, Sitle. Right. A chosen shirt and trouser must hang together. So if it's that has to hang together, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So shirt and trouser must hang together. That's 2 factorial by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factorial. Okay, that's the number of ways in which that can happen. Does that make sense to everybody? That's what we were doing earlier as well. Okay, so here that gives us 7,257,000, I think, 600. Okay, let's just see where you guys are at. Okay, no problem. So the shirt and the trouser are hanging together. So this is like what we were doing over here with the boy and the girl. Okay, so remember when we were putting the boys together in a group and then arranging the boy group with the other girls? Or putting the girls together in a group and then arranging them with the boys? It's the same idea. Okay, so we're putting a shirt and a trouser together in a group. Okay, so this shirt and trouser have to stay together. There are 2 factorial ways in which they can be arranged, because it's either shirt trouser or trouser shirt. If a shirt and a trouser are now together in a group, they can now be combined in 10 factorial ways with the others, because look here, there's 1, 2, okay, ignore these numbers now because we're using this for something else. 3, 4, 5, 6, 7, 8, 9, 10 groups. Okay, so there are 10 factorial ways in which the shirt and trouser pair can be arranged with the others. That's why it's 2 factorial by 10 factorial. Does that make more sense now? Hope so. Okay, good stuff. All right, are there any last questions on what we've done this evening? Yolanda's putting in the course there, the quiz for you guys.
Yes, that's the quiz.
Slip it in there quickly while you can, Yolanda.
Oh.
No, Jude, because when the shirt and the trouser goes together as one thing, there are 10 groups. To the toboggan, what? Okay. No problem. I'll go back to the toboggan. So Jude, if in doubt, just put circles around them and then count how many circles you've got, how many groups you've got. Okay, just hang on a second. Why isn't E multiplied by 2 factorial again? Oh, it could be. It could be. No, hang on a second. A shirt and trouser must be hung together. No, it wouldn't need to be multiplied by 2 factorial again. No, it wouldn't. Okay, so the toboggan question, where were we? I think it was up here. There we go. There's the toboggan question. It's question number 6. Okay. So remember, with the toboggan question, there are 6 people riding in the toboggan. But there's only a choice of 3 people, one of 3 people that can fill the driver's seat. So there are 3 ways in which the driver's seat can be filled. When the driver's seat has been filled by one person, one of the 3, there are now 5 people left. So that's why it's 3 by 5 factorial. Okay.